Okay, welcome to the Riemann Sum video. This is such a big topic that I made it separate from the review. So say we have a curve, and I asked you to, without using calculus, estimate the area. Here are four ways to do that. First, using right rectangles, where the height is the right endpoint. Alternatively, you can use left rectangles, which are rectangles where the height is the left endpoint. Midpoint rectangles are rectangles where the height is the average of the right and left endpoints. Or you can use trapezoids. For all of the four methods, notice that as the number of quadrilaterals increases, the approximation gets better and better. Here are formulas for the four methods. If the bases are equal, the approximation for the right endpoints is going to be the base times each of the right heights. For the left rectangles, just replace the right endpoint with the left endpoint. However, if the bases are different, you're going to have to multiply each individual base times each individual height. For the midpoint rectangles, the height of f is going to be the average of the two x values. And then finally for the trapezoids, the area will be 1/2 times the base times the sum of the heights. These sums are called Riemann sums. Well, at least according to Khan Academy, these three are called Riemann sums, and this one is just called a trapezoidal sum. I don't really know. And then, before we go into the next section, I just need to review summation formulas. If you're summing from 1 to n of a number c, that sum is going to be Cn. For a variable I, which by the way is just a variable here, I is not equal to the square root of -1 in this case. I is just a variable that we're using. So if we're summing from 1 to n of I, it's going to be n times n plus 1 over 2. If we're summing I squared, it's going to be n times n plus 1 times 2n plus 1 over 6. And then for I cubed, it's going to be n times n plus 1 over 2 whole squared. We're going to need those going forward. So if I wanted to estimate the area under the graph from 1 to 2 by drawing rectangles, I'm going to need some formulas. First, the x value of the endpoints are going to be, for the ith endpoint, it's going to be a plus I delta x, where I is going to be some number. A is going to be this distance from the origin to where we're starting, from 0 to 1. And then the area for the total, for each rectangle, is going to be, that's area, is going to be f of that ith point, which is the height, times the base, which is delta x. The total area is going to be the sum of the rectangles, all the rectangles added together, and as the number of rectangles approaches infinity, the estimation becomes more accurate. Therefore, I can write the limit as n approaches infinity of the sum of the area for each rectangle. And this is the exact area. This is also the limit definition of the definite integral. And then the delta x here is going to be my final point, b. So this is going to be my b, minus my initial point a, this is my a, over the number of rectangles. Here's a concise list of everything we said so far. Okay, so this is the graph of y equals x squared, right? So since the ith endpoint is going to be a plus I delta x, like we said, and then since f of x is equal to x squared, our f of I is going to be a plus I delta x squared. In our case, a is going to be 1 since we're starting at 1. We also need the delta x, so a is 1, and then the delta x is going to be my final point minus my initial point over n, which is 1 over n. So plugging this into our limit form is going to give us this. Now, we're going to expand this formula. We're going to expand this part here by using the formula for a plus b whole squared. And that's going to give us this. And then, we can use the summation formulas to write the I in terms of n. For example, replace the I with n times n plus 1 over 2, etc. And for the 1 over n part, since there's no I, just treat it as a constant and multiply it by n according to the summation rule for a constant. Notice that this is the point, this third step, where the summation symbol is dropped, because when we replaced the i's with the n's, we did the summation part, and now we only have the limit part left. Then, since we're taking the limit and all the powers are equal, look at the coefficients. Here, it's going to be 1, and 1, and 1/3. Adding these up gives us 7/3. These problems can get extremely algebraically complicated, but following the steps and then looking at the coefficients makes the process as easy as possible. Don't expand the numerator up here, because that's just going to be a huge waste of time. Since the integral is the area under the curve, we can also say that the integral from 1 to 2 of x squared dx is equal to our limit that we made, the limit of the sum. Because remember, this limit is basically the formula that we use to calculate the definite integral. And both of these are equal to 7/3. Okay. Another type of problem you might see is going between these two forms. If you're given the integral, you might find delta x by b minus a over n, and then you might find xi by finding a plus I delta x, and then you're going to put those together. You might also have to go from the summation to the integral. Here you have your delta x, and you know that b minus a equals 1, since the coefficient here is just 1. Also, looking at this part, you know that a equals 1. Therefore, you can say that b equals 2. So we know that the integral goes from 1 to 2, and it looks like for this f of x part, it's something being squared, so we can probably say that the function is x squared dx. Therefore, this limit is equal to this integral. So now we're going to move on to the problem solving portion of this video, where I'll give you 3 problems, and you can pause and give it a try before I show you how to do it. Okay, so the first question, use the limit definition of the integral to find that. And it's a really nice shortcut is if you just graph this function from -1 to 1. Notice we have these two areas under the graph. Those are opposite in sign. This one's negative, this one's positive, but the areas are going to be equal. So if you added those two up, you're going to get 0. Right? So we can already tell beforehand that the answer is going to be 0. But let's prove that using the limit definition, because that's what it asks for in the question. So our function f of x is x cubed, and then we're going from -1 to 1. Okay, so let's find the delta x. It's going to be b minus a over n, which is, or b is 1, or a is -1, so it's going to be 2 over n. And then the x sub I, the formula is a plus I delta x. Our a is -1. Our delta x is 2 over n, so our I delta x is 2i over n. And then so these are two of the pieces of the problem, our delta x, and then our x sub I. So we're going to use those two pieces to figure out the limit definition. So remember, the limit definition has f of xi delta x, and then f of x is x cubed. So if we replace the xi in for the x, we can plug in the -1 plus 2i over n into our function. So we're going to get -1 plus 2i over n. I'm replacing x with this, and then I'm cubing it, and then I'm multiplying it by the delta x, which is 2 over n. Okay, so now the next step is going to be to expand this using the binomial theorem, or if you memorize the formula for that, you can use that. And so it's probably a good idea, since you might see a problem like this, to spend a couple minutes, know the binomial theorem, so you can save a lot of time on your exam and stuff. So let me just write that down. Okay, so I've expanded it out, and I've also written the summation formulas because we're going to use those in a second. And then the next step is going to be multiplying this whole thing by 2 over n. So that's going to be negative 2 over n plus 12i over n squared minus 24i squared over n cubed plus 16i cubed over n to the 4th. And remember, we're not finding this, we're finding the sum of the limit of the sum. So the full problem is asking the limit as the number of rectangles approaches infinity of the sum of this stuff here. The sum of that stuff using copy and paste magic. And then, so now what we can do is we can say, okay, so this is just, we can look at the I here and say, since we're finding the sum, we can use this formula over here. If we're finding I, that's supposed to say I squared, we can use this formula over here. And then this, I cubed, we can use this formula down here. Let's move down a bit. Okay. And then when we're going to plug those in now, and then we'll see what we'll get. Okay, so I've expanded that out, and also notice that now I dropped this the sigma, because remember when we plug in the n's for the i's, we did the summation part, and now all we have left is the limit part. So let's just look at the coefficients here. We're almost done. The coefficient for this n's are going to cancel, we're going to get negative 2. The coefficient is going to be 12 over 2 is going to be 6. The coefficient is going to be 24 times 2 divided by 6, which is going to be, well, it's actually going to be a minus. So we're going to have minus 8. And then we're going to have 16 over 2 squared. So it's going to be a 4. And then so we have negative, so we have 4 minus 8 is negative 4. The negative 4 plus 4 is 0. Okay, welcome to question 2. So in this question, we're going to use the limit definition of the definite integral to find an expression for this function. I'm not going to evaluate it, just find it. So remember, the limit definition of the definite integral is the limit of the sum of that. Okay, so let's find each of those two parts. Let's start with finding delta x. That's going to be b minus a over n, or b is 1, or a is 0, so this is 1 minus 0 over n, or 1 over n. That's part 1. Part 2, f of xi, right? Let's find x sub I first. X sub I is going to be a plus I delta x, or a is 0, and then our delta x is 1 over n, so this is just going to be I over n. Okay, and then f of xi, that's going to be whenever we see an x in our f of x up here, whenever we see an x, we're going to replace it with I over n. So this is going to be 6 times I over n times I over n minus 1. Right, that's part 2. And then now we can write the limit definition. Since we have both the parts, we'll say the limit of the sum, and then the f of xi, it's going to be 6i over n times I over n minus 1 times our delta x, so times our 1 over n. And with that, we have finished problem 2. Okay, question 3. Now we're going the other way. we're given the limit definition and we need to write the definite integral. So let's look at part A. We're going to find first the delta x, which is this part right here. It is b minus a over n, and it looks like that is equal to pi over n. We can cancel the n's, and we can say b minus a equals pi. And then from this part, we see that x sub I, which is a plus I delta x, is equal to e plus pi I over n, and then the a is e. So we know that a is e, and then plugging that into here, b minus e equals pi, b is equal to pi plus e. And these are the bounds of our definite integral. So the integral is going to go from e to pi plus e. And then for the actual function, looks like we're having something here being raised to the negative pi power. This is our f of x part, right? So it's something being raised to the negative pi power. So our function is going to be x to the negative pi power, and then a dx on the end. So this is going to be the part A. And now let's look at part B, which looks at first glance very, very similar, but the only difference is that now only the pi I over n is being raised to the negative pi power. So again, the first part is going to be the same. The delta x is b minus a over n, which equals pi over n. Cancel the n's. b minus a is equal to pi. But now look, we have a constant e plus this thing being raised to the negative pi power. This is really the x part of the function. This is just another constant that's along for the ride, but this is the x, and then so our x sub I is only going to have the pi I over n plus, there's nothing being added, it's just adding 0. So our a is 0 actually here. A is 0, so b is going to be pi. So that means in our definite integral, so let's go down, there we go. The integral is going to go from 0 to pi, and then going up. Our function is just e plus something to the negative pi power, so it's going to be e plus something x to the negative pi power, and then to show the dx. So that is our answer for part B. And with that, we're done with the entire Riemann sum video. I hope you found the video explanations and the problem helpful. If you did, say something, I guess, and I'll see you next time. Okay, so I know I said there's only going to be 3 problems, but I realized I forgot to do a problem involving left hand, right hand, that kind of sums. So I just added another problem on it, and we're going to roll with it. So we're given the function f of x equals sine x. We know that the integral from 0 to pi of sine x dx equals 2. And then, which of the following methods would yield the most accurate estimate of that integral? So it looks like it's a multiple choice question. We're given 3 different possible sums, all with 3 rectangles. And we need to find out which of these 3 is the closest to 2. So let's evaluate part A. So if we graph sine of x, I'll just graph it here. From 0 to pi, it's just going to look like that. And then since we're splitting it up into 3 parts, we're going to have pi over 3, 2 pi over 3. Right? So a left-hand sum, that's going to be where we have this first height starting at 0, and this second height starting at sine of pi over 3, and then this third height starting at sine of 2 pi over 3, right? So we're going to add all these 3 up. So the way I'm going to do it is it's going to be pi over 3 times the height at each of these 3 places. So the height is going to be sine of x, so it's going to be sine of 0 plus sine of pi over 3
plus sine of 2 pi over 3. Right, this is the formula. Since they all share a common base of, since it's equal like steps, then it's going to be pi over 3 times the left hand height. So sine of 0 is just 0. Right, sine of 0 is 0. Sine of pi over 3 is square root of 3 over 2. And then sine of 2 pi over 3, since that's in the second quadrant and sine is positive in that quadrant, this is also the square root of 3 over 2. Adding these three up, that's going to be pi over 3 times the square root of 3, or square root of 3 pi over 3, like that. So that's part A. And now let's look at part B, a midpoint sum with three rectangles. So now a midpoint sum is going to be, instead of having it like this, it's going to be, the height is going to be the height of the midpoint. So it's going to be this value right here, and then instead of here over here, it's going to be this value right here. That's oh god, that looks okay. And then instead of here it's going to be this middle point ish right there. Terrible drawing, I'm sorry. Something like that. Try to make it look good. So anyways, it's going to be, the formula for that is pi over 3 times sine of the average of the two points. So first it's going to be the average of 0 and pi over 3, which is 0 plus pi over 3 over 2, plus sine of the average of these 2 points, so pi over 3 plus 2 pi over 3 over 2, plus sine of the average of these 2 points, so 2 pi over 3 plus pi over 2. And then let's see, so pi over 3 over 2 is going to be pi over 6. And then so pi over 3 plus 2 pi over 3 is just pi, and then pi divided by 2 is pi over 2. And then sine of 2 pi over 3 plus 5 is 5 pi over 3, so that divided by 2 is 5 pi over 6. Okay, let's evaluate these. So sine of pi over 6 is 1/2. Sine of pi over 2 is 1. And then sine of 5 pi over 6, that's reference angle of pi over 6, and it's in the second quadrant, so it's going to be 1/2 as well. Therefore, these two add up to, this 1/2 plus 1 plus 1/2 is 2, so the total is 2 pi over 3. Okay, that's for part B. And now let's look at part C. Yeah? Part C asked for, I think it said trapezoidal sums. Yeah, trapezoidal sum with three rectangles. So what that's going to look like is, let's see, I'll choose red. It's going to be a trapezoid starting from here going up to there. It's going to be like a triangle, and then we're going to have another triangle. We have another triangle like that. So we have these three like triangles slash trapezoids, and then we need to find those areas. So let's see what we can do. That's going to be 1/2 times the base, so pi over 3, times, okay, so for trapezoidal sums, it's going to be sine of the left plus sine of the right, 0 plus pi over 3, so plus, and then plus sine of pi over 3 plus 2 pi over 3, or no, plus, sorry, not plus 2 pi over 3, plus sine of 2 pi over 3, and then finally plus sine of 2 pi over 3 plus sine of pi. And going back to the picture, the visual we drew earlier, That's going to be this, the height here plus the height here, and then the height here plus the height here, and then the height here plus the height here. Yeah? So let's evaluate all these things. This is going to be, so pi over 3 times 1/2 is pi over 6. And then sine of 0 is 0. Pi over 3, sine of pi over 3 is square root of 3 over 2. Again, square root of 3 over 2. Sine of 2 pi over 3 is square root of 3 over 2. Okay? Plus sine of 2 pi over 3 is square root of 3 over 2. Seeing a pattern here. And then sine of pi is again 0. So adding all these up, so it's going to be 2 times square root of 3. So pi over 6 times 2 square root of 3. It's going to cancel. I'm going to get 3. So this is square root of 3 times pi over 3. Right? So we got for part C. And now let's compare let's summarize our answers real quick. Okay, summarize the answers. And interestingly enough, it seems that part A and part C have the same answer. Okay, so now we want to evaluate these, like get a decimal, and see which one is closest to 2, yeah? So with part A, it's going to be square root of 3 times pi divided by 3, which is 1.814, or 8138. And then part B is 2 pi over 3, which is 2.0944. And then part C, well, we already said it's 1.8138. I mean, technically, you don't even have to do this out. These both can't be the answer, so it was obviously going to be part B. But again, looking at this, it's clear that part B, the midpoint sum, gave us the best estimate of the sine, the integral, because 2.09 is a lot closer to 2 than 1.8 is. And I don't know if this is concretely true or not, but I feel like a lot of the times the midpoint sum is one of the most accurate types. I'm not sure if that's actually true, I'm just like guessing. But anyways, so I promise you now we are done. We did the last problem. I hope you found that helpful, and I'll see you in the next time. See you in the next one. Goodbye.